Hello, everyone. Today I'll be presenting on the constinit keyword in C++. This feature was introduced in the C++ 20 standard. Constinit provides compile time initialization for variables with static storage duration. It offers some interesting capabilities that we'll explore in this presentation. Constinit addresses specific challenges in C++ programming, particularly around initialization order and performance. It provides a middle ground between the strictness of constexpr and the flexibility of regular variables. Let's start with the basics. Constinit is a specifier introduced in C++ 20. It ensures that a variable with static storage duration is initialized at compile time. When we say static storage duration, we're referring to global variables, static class members, and static local variables. These are objects that exist for the entire lifetime of the program. The key distinction here is that constinit guarantees compile time initialization, but it does not imply constness. This means the variable can be modified at runtime. This is fundamentally different from constexpr, which we'll compare in detail later. Constinit essentially tells the compiler, initialize this at compile time, but don't make it constant. This comparison table highlights the key differences between these three specifiers. Notice that constinit guarantees compile time initialization like constexpr, but unlike constexpr, it allows runtime modification. Also important is that constinit variables cannot be used in constant expressions, while constexpr variables can. This makes constinit suitable for different use cases than constexpr. The const specifier, on the other hand, only guarantees immutability at runtime. It doesn't guarantee compile time initialization. In fact, a const variable with a runtime initializer will be initialized at runtime, which can lead to the static initialization order fiasco. Understanding these distinctions is crucial for choosing the right specifier for your specific needs. Looking at the syntax, we can see that constinit requires a constant expression as an initializer. The first example shows a valid declaration with a literal value. Constinit int x equals 42. This works because 42 is a constant expression. The second example shows an invalid attempt to initialize with a runtime function call. Int runtime_func, then constinit int y equals runtime_func. This fails because runtime_func is not a constant expression. On the right, we see how constinit solves the static initialization order fiasco. The fiasco occurs when the initialization of one static variable depends on another static variable in a different translation unit, and the order of initialization is undefined. By ensuring compile time initialization, constinit eliminates this problem because the values are embedded in the program binary. There are three main benefits to using constinit. First, performance. There's zero runtime overhead since initialization happens at compile time. The variable's value is directly embedded in the program's data segment, avoiding the cost of dynamic initialization at program startup. Second, determinism. It solves the static initialization order fiasco by guaranteeing a specific initialization order. This is particularly important in large code bases with many translation units. Third, thread safety. Variables initialized with constinit are safe for concurrent access without additional synchronization. This is because static initialization happens before any threads are created, so there's no race condition when multiple threads try to access the variable. These benefits make constinit particularly valuable in performance-critical code and multi-threaded applications. Like any feature, constinit has limitations. It can only be used with variables that have static storage duration. You can't use it with automatic or stack variables. It requires a constant initializer, which means the initializer must be a constant expression or have a constexpr constructor. And there are some caveats with non-trivial destructors. While constinit ensures compile time initialization, it doesn't affect destruction. If a constinit variable has a non-trivial destructor, that destructor will still be called at program exit, which can reintroduce some of the ordering issues that constinit was designed to avoid. The key takeaway is that constinit provides compile time initialization while allowing runtime mutability, bridging the gap between constexpr and regular variables. It's not a replacement for either, but rather a complementary tool for specific use cases. Constinit can also be used with references and pointers, though with some specific requirements. For references, constinit is equivalent to constexpr. This is because references themselves are not objects, but rather aliases to objects. When we declare constinit constint reference ref equals 42, the const is required because we're binding to a temporary, and C++ requires that references to temporaries be constant. For pointers, they must bind to constant expressions with static storage duration. For example, constinit int pointer ptr equals nulpture is valid, as is constinit int global equals 42. Then constinit int pointer ptr 2 equals address of global. However, int runtime equals 10. Then constinit int pointer ptr 3 equals address of runtime is invalid because the address of runtime is not a constant expression. Understanding these rules is important for correctly using constinit with reference and pointer types. When combined with thread_local, constinit guarantees compile time initialization for each thread. Thread local storage is a mechanism where each thread has its own separate instance of a variable. Without constinit, thread local variables are initialized when they're first used by each thread, which can add runtime overhead and potential race conditions. With constinit, the initialization happens at compile time, so each thread gets its pre-initialized copy without any runtime cost. The syntax is straightforward. Constinit thread_local int x equals 42. This guarantees that each thread's copy of x is initialized to 42 at compile time. The benefits include 0 runtime overhead, no initialization check on first use, thread safety with no race conditions during initialization, and predictable behavior in multi-threaded contexts. This makes constinit thread_local particularly useful for performance-critical multi-threaded applications. Constinit is a C++ 20 feature, so you'll need a compiler that supports this standard. GCC 10 and above, Clang 10 and above, and MSVC 19, 28 and above all support constinit. You'll also need to use the std equals C++ 20 compiler flag, or stdc++20 for MSVC. The __cpeep_ constinit feature test macro can be used to check for support in your code. For example, if defined __cpeep_ constinit, then constinit is available, else constinit is not available. It's worth noting that compiler support may vary in earlier versions, so always check your specific compiler's documentation. Additionally, some compilers might have partial support or subtle differences in implementation, so thorough testing is recommended when first using constinit in your codebase. In real-world applications, constinit is particularly useful for global configuration objects, singleton patterns, and logging systems. For global configuration, you might have a config object that needs to be accessible throughout your program, but might also need to be modified at runtime based on command line arguments or configuration files. For singleton patterns, constinit can help avoid the double-checked locking pattern and its associated complexities. For logging systems, you might have a global logger that needs to be accessible from multiple threads without synchronization overhead. When deciding whether to use constinit, consider if you need static storage for global or static variables, runtime mutability, where you need to change the value after initialization, and zero initialization overhead for performance-critical code. For debugging, use the __cpeep_ constinit macro to check for compiler support and carefully check compiler errors. The compiler will tell you if an initializer isn't a constant expression. Remember that constinit is not a silver bullet. It's a tool for specific situations where you need compile time initialization, but also need runtime mutability. Constinit can be used with class types, but only if they have constexpr constructors. The example shows a valid config class with a constexpr constructor. Struct config with constexpr config of int v, initializing value of v, then int value. Then constinit config cfg of 42. This works because the constructor can be evaluated at compile time. However, classes with non-trivial destructors still get dynamic destruction, even if they have constexpr constructors. This is an important limitation to be aware of. For example, if config had a destructor that did something non-trivial like freeing memory or writing to a log, the destructor would still be called at program exit, potentially reintroducing order dependencies. In practice, this means that constinit with class types works best for simple aggregate, like classes, without complex destructors. If your class needs a non-trivial destructor, you might need to consider other approaches, such as using a function with a static local variable, known as Myers singleton, or explicitly managing lifetime through other means. To summarize, constinit provides compile time initialization with runtime mutability, making it ideal for cases where you need static initialization but also need to modify the variable later. It's particularly useful when you need to avoid the static initialization order fiasco or require thread-safe initialization without runtime overhead. The key points to remember are: constinit guarantees compile time initialization, but unlike constexpr, it allows runtime modification. It can only be used with static storage duration variables. It requires a constant expression as an initializer, and it doesn't affect destruction, so non-trivial destructors can still introduce ordering issues. When choosing between constinit, constexpr, and const, consider your specific needs. If you need immutability and compile time evaluation, use constexpr. If you need runtime immutability, use constant. If you need compile time initialization with runtime mutability, use constinit. Understanding these distinctions will help you write more robust and efficient C++ code. For further reading, I recommend consulting the official ISO C++ standard, which provides the authoritative specification for constinit. The original constinit proposal P1143-R2, titled Adding the Constinit Keyword, provides valuable insight into the design decisions and rationale behind the feature. The preference. COM documentation offers a more accessible explanation with examples. Compiler-specific documentation from GCC, Clang, and MSVC can provide implementation details and any compiler-specific behaviors. There are also several C++ conference talks and articles available online that discuss constinit in more depth, including real-world use cases and performance considerations. I particularly recommend C++ Weekly Episode 195, which provides a practical introduction to constinit. These resources will help you deepen your understanding of constinit and how to effectively use it in your C++ projects. That concludes our presentation on constinit in C++. Thank you for your attention.